We've got a scenario here, and we're told that OQ is the diameter. So I'm going to put that straight in. And so the center would be sort of around here. Now there's a circle theorem that says when you have an angle in a semicircle, you get a right angle. So this must be a right angle. So I'm just going to write down angle OPQ equals 90 degrees. Angle in a semicircle. Now we're asked to prove that P dot Q is equal to the modulus of P squared. So the general formula is this. And let's just add on. So the position vectors of P and Q relative to O are that. So this here is P and this is Q. And that angle is theta. Now in this one, Q is actually the hypotenuse, and so we could actually write down that cos theta is equal to the adjacent, which is the magnitude of P, divided by the hypotenuse, which is the magnitude of Q. And therefore, the magnitude of P is actually the magnitude of Q cos theta. You might have got this more quickly if you're familiar with your mechanics. It's sort of we're basically splitting it into two parts. And this one goes towards the angle, so it's cos, whereas this would be sine over here. So we're going to get, we can just replace it. It's going to be P times the modulus of P, and we get the result that we were asked to prove. Okay, good start. We're then told some more information about this circle. We've got the point R, which also lies on C, and these are equal lengths. This is a diameter, so this will also be a right angle. And then there's a point S that has position vector relative to O of lambda Q. So that means it's going to be somewhere, S is going to be somewhere along this line. We're also told, however, that OQ is perpendicular to PS. So if I draw that line in, OQ is perpendicular to PS, then we also get a right angle here, and this is S. We want to work out so this here is lambda Q, and we want to work out the value of lambda. Note we're given the vectors P and Q. Now, one thing that springs to mind is that we could find the dot products that we've already kind of dealt with it up here. So that would allow us to find the angle theta. And if we know theta, we can use this length and we can hence find this length here, which will tell us lambda q. So the first thing I'm going to do is I'm going to work out let me do this in green. It's going to work out the magnitude of P. So it's going to be the square root of 1 squared. I'm just using 3D Pythagoras on this vector. 1 squared plus 2 squared plus minus 1 squared, which is also 1 squared. That will be root 6. Whilst root q is 2 squared plus 1 squared plus minus 2 squared. Again, we can just write 2 squared. So that will be 3, because 4 plus 4 plus 1 is 9. So P dotted with Q is equal to the magnitude of P squared from A, which will equal 6. And it's also going to equal root 6 times 3 times cos theta. That's using the, your normal form here, and so it's in terms of q. Therefore, cos theta will equal, if I divide by 3, I'll get 2. So it's going to be 2 over root 6. And hence we can therefore work out, we can write down that cos theta is also going to be the magnitude of lambda q over the magnitude of p, which is root 6, and that is going to equal 2 over root 6. By the way, the magnitude of lambda q is going to be lambda times the magnitude of q, so we can write lambda times 3 is equal to 2. I've just cancelled out these root 6's, by the way, and I've got lambda here, and I've just times by the magnitude of q. So therefore, lambda is equal to 2 over 3. Just before we move on, I want to show you another method that you could use to get this value for lambda, and that is because using the fact that PS is perpendicular to OS, or even OQ. So this is a method 2. So this would imply that PS dotted with OQ is equal to 0, because the angle is 90 degrees, cos of 90 is 0. Now PS, the vector, we could get by doing minus P plus lambda Q. And then if we dot that with OQ, it's just dotted with Q like this. Now, when we have something like this, you can basically, you can dot product this with this and this with this and just add them together. So we get minus P dotted with Q plus lambda Q dotted with Q is equal to 0. From before, this becomes minus P, the magnitude squared. Okay, that was from part A, plus lambda Q squared equals 0. So lambda is equal to P magnitude squared over magnitude of Q squared. And then we can sub in, like obviously we had to have worked these out, but we're going to get 6 over 9, which is again 2/3. So I don't know which method's better, they're just different, but they both give the same answer. Let's take a look at part C. There's a lot of parts to this question. Find the position vector of R. And on here, I've drawn a line going down. And so we're trying to find OR. We can get OR as a vector by going OS and then adding SR. Now OS, remember, is lambda Q, so it's going to be 2/3 times Q plus SR, and SR is exactly the same as PS. And then remember, we were just talking about PS. It was minus P plus lambda Q. So it's going to be another lambda Q, and then I'll put the minus P here, which gives me 4/3 times Q And q, if we look up here, is 2, 1 minus 2. Minus p, which is 1, 2 minus 1. I'll just write these out as fractions. Then I'm minusing a minus, so I'm adding. So this is the position vector of R. In part D, we're asked for the area of the kite. So what we could do is find the area of one of these triangles and then double it. Now we can either do the OQ times SP and times it by a half and then by 2 for the other one. Or because we have a right angled triangle, you can actually imagine sort of turning it round. And this would be the base and PQ would be the height. Now we have that this length is equal to root 6, and then this length is 3. So we can work out PQ using Pythagoras Theorem. Remember, this is going to be the hypotenuse, is 3. So PQ that is going to be 3 squared minus root 6 all squared, square rooted, which is 9 minus 6 square rooted, which is root 3. Therefore, area of K is going to be, if we do a half base times height, we'll get a half times this root 3 times root 6. But of course, we then double it. These cancel, and we're just going to be left with, well, we could write it as root 18, or we could write it as root 3, root 3, root 2. If we split that root 6 up, which is going to give 3 root 2. This leaves 2 parts of the question left, and we're on to the hardest part now, E. So we're told that another circle, C1, is drawn inside the kite so that the 4 sides of the kite are each tangents to C1. Find the radius of C1, given your answer in the form root 2 minus 1 times root n, where n is an integer. Well, I have a little bit of an advantage here because I can make exact copies and I can even draw an accurate circle inside. So that is looking pretty good. I'm going to redraw O to Q. And here I've got the center. So because it's a tangent, this length is R. Now we can also add that this is a right angle. Remember, we already know that that is a right angle. And if we draw another tangent to the circle here, we'll actually get a square. We can add on this angle here, theta. And then we can start to think about what is going on now. Because this is a square, then this length is R because it's the radius. But that means that this length must also be R. If that's the case, then this length, well, the whole thing was root 6, So this must be root 6 minus r. And what we have now is a right-angled triangle, because this is also a right angle. I'm just going to shade the right-angled triangle in purple. And we can write down that we don't have information on this, on the hypotenuse, unfortunately, because it's r up to, like, it's r up to here, but we're not using this r here is this bit. So I can't use this purple bit. I can use tan of the angle is the opposite over the adjacent, which is this bit. So ignore the hypotenuse, root 6 minus r. But we also know from before that PQ is root 3 and OP. So I'm using like the smaller triangle in purple, but then I'm using the bigger triangle OPQ. And then remember, OP is actually root 6. So I'm just going to go through that one more time before, because actually we've now got an equation in terms of r and I can solve for it. Right, I have my big circle, the kite. I've drawn another circle inside where these parts of the kite are tangents. I've drawn two of the tangents in. This green one here, okay, going to the center, and then this one to here, both with length r. Now I'm going to have right angles here and here. I already know that I've got a right angle here, OPQ, from before. So this must be a square, and that must also be 90 degrees. If it's a square, then this length, this dotted green line, is also r, which means that this point here to P is r as well. And I can write down that O to that point is root 6 minus r, because the full length was root 6. Why have I done that? Because now I've got a right angle triangle in purple with an opposite of r and an adjacent of root 6 minus r. So I wrote down tan theta and got it in terms of r, and I related it to the larger triangle, and I know that it's root 3 here. We figured that out before, divided by root 6. Okay, so I hope you're happy with that. Now we can simplify this. So r over root 6 minus r will equal, I can divide by root 3, 1 over root 2. We knew there was a root 2 in the answer. I'm going to cross multiply. So root 2r is equal to root 6 minus r. Add r to both sides. R plus root 2r is equal to root 6. Factorize out the r. 1 plus root 2 equals root 6. And we're nearly done. Let's just look at what the answer asked us for. So find the radius, root 2 minus 1 over root n. Root 2 minus 1 over root n. Sorry, times by root n. Right, so r is going to equal root 6 over root 2 plus 1. We're going to need to rationalize the denominator here, so we times by root 2 minus 1 over root 2 minus 1. When I do that, I will get root 2 minus 1 times root 6. And then on the bottom, I'm going to get 2 minus 1. So actually, this just cancels to give 1. And we've got our answer. That is the radius of the smaller circle. That is tough, and I applaud you if you managed to do that. This leaves us with the final part, way back up here. A second kite, K1, is similar to K and is drawn inside C1. Find that area of K1. Okay, I'm going to do this in black, I think. So inside it, we're going to have look a little bit like this. Now remember, we know the area of the big kite. I've forgotten what it was, but here we are, 3 root 2. So the area is going to be 3 root 2 multiplied by an area scale factor. So we know that like the length scale factor between the two kites is basically going to be the same as the length scale factors between the circles. So we have the radius of the big circle, because remember OQ was equal to 3. So do you know what? I just need to put a little bit extra in. Radius of C is equal to 3/2. Radius of C1 is equal to root 2 minus 1 multiplied by root 6. Therefore, length scale factor is going to be the smaller one divided by 3/2, which is the same as timesing by 2/3. That's between the circles. But more importantly, between the kites as well. So the area scale factor is going to be this squared. So we square this one, square this one, square these. And the area of K1 is going to be this area scale factor multiplied by 3/2. So we can partially cancel this down. I can do 6 times 3, 18, divided by 9 to give 2. 4 divided by 2 is, no, hold on. I times that by 4, so I'm going to have 8 root 2 minus 1 squared. All right, these last two parts, wow. Good effort.